Now, nonpolar covalent bonds. This is actually kind of important. You see, when atoms share electrons equally, like in this case right here between these two hydrogen elements, they create a compound that has no net electrical charge to it. Everything is kind of evenly distributed about it. These two electrons here are actually circling around these nuclei equally. And if they're circling equally, then as far as other things around it are concerned, this hydrogen gas molecule is actually very stable. So hydrogen gas is an example of a stable, non-polar covalent bond. But they're not all like that. Here's an example of one that is very strongly polar. This is water again, and we visited water. Remember that water is an oxygen atom that is sharing a pair of electrons with a hydrogen here and sharing a pair of electrons with a hydrogen here. It also has two pairs of electrons here and two pairs of electrons here that are not being shared with anything. So it is actually following this tetrahedron shape also. It's just that there's nothing coming out of these two sides except for a halo of electrons, of paired electrons. So this is not an equal distribution. It's very asymmetrical, isn't it? When you say this is asymmetrical compared to that hydrogen molecule. And so because of its asymmetry, it becomes polar. That is, if you were to just kind of let this thing fall on your desk and spin around, this side of the molecule tends to have a slightly negative charge to it. This side of the molecule tends to have a slightly positive charge to it. That is to say that the electrons are spending a disproportionate time on one side of this molecule compared to the other. And it ends up with an imbalance. This thing ends up looking like a battery. Water is the classic case of a polar molecule, where the oxygen actually ends up attracting things around it that are positive because it is so negative on this side, and the hydrogens end up attracting things that are negative because it is slightly positive on its side. And the attraction is called electronegativity. Okay, so electronegativity is actually why water molecules, or water element, the water that you actually drink, is so stable and hard to break apart. Water is truly amazing stuff. You see, the more electromagnetic an element is, like water, the harder it pulls on other things, which is why water is so good at washing your hands, or washing your clothes, or why it's able to break apart salt so easily, because of that really strong polar properties, that electronegative property of water. So yeah, as I mentioned, water is incredibly stable. The fact that they are sharing these electron pairs here, one over here and one over here, combining them, makes them really, really, really stable. But take a look at this pair of electrons here and the pair of electrons here. Because they're not attached to anything, it's almost like they're circling wildly and crazily. And so where a tetrahedron normally would have an angle of 109 degrees, these electrons here are actually forcing these hydrogens even closer together so that their angle is actually 104.5 degrees. Again, this 104.5 degree angle is squeezing together away from that 109 because of these electron clouds over here on this side. And it is extremely important because if this property didn't exist in water, if this angle was not 104.5 degrees, water would be a solid on planet Earth. Thank goodness it's not. Thank goodness it's not. So hydrogen bonding is actually very important in water. Remember, polar molecules attract things of opposite charge to the atom. And since water molecules are polar, they attract other water molecules. And so water ends up taking on this, it's almost like a lattice. It's almost like an electronegative lattice. And for that reason, water has some really interesting properties. In fact, they have very interesting biological properties, like cohesion. Sticking, that is, water sticks to itself so well that insects can actually walk across it. The water does not break, and therefore the insect doesn't fall through because the water molecules are so attracted to each other. On the hood of this car, for example, the water actually balls up and beads up because it's attracted to itself. Water also has a very high temperature stabilizing effect. When you add a huge amount of energy to water, it actually takes a lot of energy to change the temperature of water. You actually know this to be true. When you turn on a pot of water and you bring it to a boil and you turn it off, let's wait a minute or two. You wait a minute or two and then you pour it on your hand and you're still going to be burned because the water retained the heat and it didn't give it up very easily. You can do the same thing with icy water too. Put your hand in icy water 10 minutes after you made the icy water and it's still darn cold, isn't it? Now, water, again, because it's so polar, it actually has a really high ability to dissolve substances like salts. We've brought that example up now a couple of times. And freezing effects. Water does something very interesting when it freezes, doesn't it? When it freezes, unlike other solids like rocks, it floats. It doesn't sink. Okay, not all other compounds do that like water. Water is unique in that when it's frozen, it's actually lighter than the liquid form of it. So that's really weird. So let's go ahead and just talk very briefly about some of these. Again, surface tension and cohesion, great example of things kind of floating on the surface there. This is because of those strong hydrogen bonds. Water is hydrogen bonded to itself so strongly that it won't let anything puncture through it. And another good example, water sticking to itself and to other surfaces. Water likes to stick to itself. You can do this experiment yourself. Just take a little bit of water and pour it on your desk right now and drag your finger through it. And you will actually see that the water is actually drawn along. It's pulled along. That's called cohesion. Now, cohesion is slightly different than surface tension, but I'm not going to have you know the difference between that. As far as you're concerned, cohesion and surface tension are basically the same thing. But it is this property of water actually being able to pull on itself and able to be attracted to itself that allows a tree to draw water from the soil and actually pull it all the way to a top of a tree, which in the case of a sequoia tree can be like 200 feet. Well, it's doing that. It's able to draw the water 200 feet into the air because of the surface tension and cohesion of water. It's no different than this right here, drawing a liquid through a straw. The reason you're able to do that and the water doesn't just fall back down through the straw is because it is so highly attracted to itself. And so to the point of water actually being able to moderate temperature, this happens all the time. And water actually resists temperature change very well. It takes a lot of energy to heat water. And a lot of people use the word heat and temperature interchangeably, but they're actually not the same. Heat is actually associated with the movement of atoms and molecules. Temperature is the measurement in the change of energy or the intensity of the heat in a substance. And you're like, I don't get it. I don't understand. How are those different? Well, I want you to think about that pot of water, okay, and the fact that it takes a lot of energy to heat water. Let's try this experiment. You can do this at home. Okay, I want you to go home and turn the fire on your stove. Take your hand and put it over the fire. Okay, don't do this experiment for real, but you can do this as a thought experiment. What if you had your hand over the fire for like 5 seconds? What would happen? Yeah, your hand would totally burn. You'd probably have like second-degree burns on your hand. So that's why I don't really do this experiment. My point is that your skin, the proteins in your skin, change temperature and change heat. Change temperature with a little bit of heat put into it very rapidly to the point where it actually damages your skin. But let's take a pot of water and put it over the fire for that same 5 seconds. How much did the temperature change? Like almost not at all, huh? Right? You know what I'm talking about. If you want to change the temperature of that pot, you have to leave it over the fire for many, many minutes, right? If you left your hand over the fire for the same amount of time that it took to boil a pot of water, you wouldn't have a hand, right? So that goes to show you that heat, that when you pour the heat into your hand burns. When you pour that same amount of heat into the water, it doesn't even change its temperature very much. So heat and temperature are not necessarily the same thing, but you can actually use that property to your benefit. You can actually put your heat into liquid and then evaporate that liquid off to cool yourself. Yeah, we call that evaporative cooling. It's called sweating. Your body sweats, it's releasing water because you're starting to heat up. You're starting to gain heat, and the way to get rid of some of that heat is to put it into the water, that being the sweat, and then evaporating it off your body. That cools your body, it gets rid of excess heat. So that's kind of interesting. Now, what about its effect on dissolving substances? Water does a great job of dissolving substances. And case in point, remember this ionic compound here, sodium chloride, salt, where one gives up an electron and the other gains an electron, and it produces these two ions here, and they form a solid. They form a solid when they are kind of in proximity to each other. And however, and here's table salt, by the way, that's what table salt might look like in its crystalline form. However, if you take this salt and you were to pour it into water, this is what happens. Look at that. You see, here's the water molecules. Remember how they're polar and how these hydrogens like to attract themselves to negative things and how the oxygen like to attract themselves to positive things? Well, in the presence of water, salt doesn't hold up. It totally disseminates and falls apart because of the this polar property of water. Well, that's neat. And what about ice? Well, again, just to remind you that water is unusual in that it actually floats when it's a solid. That is a very important property of this substance on the planet Earth. If it wasn't that way, life could not exist as we know it today. Certainly could not. Another interesting property of water is that water is actually densest not at 0 degrees, right? Think about it. As water gets colder and colder and colder, it gets denser and denser and denser. Here, let's go ahead and start with water that's 20 degrees. Let's put that water in the refrigerator, and we're cooling it down, and we're cooling it. And the water's getting denser and denser and denser until it reaches this point here at which it's really, really dense. Okay, it's actually heavy. You can think of it that way. Now what happens as we chill it down? Now we're going to take it out of the refrigerator and put it in the freezer. As you approach 0 degrees, the water gets less dense and less dense and less dense until it's floating. That's kind of interesting, isn't it? It means that water is actually densest not when you get it colder and colder and colder, but actually when you get it down to right around 4 degrees. A little less than that, but we're going to call it 4 degrees for our intents and purposes. So water is extremely important stuff, and especially solid water in the form of ice. It's important that it floats when it hits 0. Otherwise, our oceans and our lakes and our streams and all the organisms living in them would be very, very different. So what about water attraction or aversion? Water is very attracted to certain substances, and it is very averse to others. When it attracts other substances, we call that hydrophilic. Hydro is the scientific term for water. Philic means to love. So hydrophilic substances are substances that like water, that have an affinity for water. Vinegar is a good example. Alcohol, great example. Juices, these are things that mix in really well with water. Hydrophobic substances are the exact opposite. Hydro, again, meaning water. Phobic, meaning averse to or afraid of. Okay? Substances that are hydrophobic would include things like oil. You can't mix oil and water. Oil is hydrophobic. Vinegar is hydrophilic. And this is a very important property that occurs in your body, and it allows us to move certain things around in your body. This is a particular molecule called a lysozyme, and it lives in an aqueous environment, and it is very attracted to water molecules. And so for that reason, it only works when there are water molecules present. Okay, let's talk about some safety issues here now too. Acids and bases. You guys have probably heard of acids and bases in your life. They are extremely dangerous. You might think, oh, acids are dangerous. Bases therefore must be okay. No, bases are just as dangerous as acids. Um, Here is a typical water molecule. And remember, water molecule, one oxygen, two hydrogens. Well, you can actually break a water molecule up into these component parts. It's actually not too hard to do. You can unbound a proton from this. So remember, a hydrogen atom is made up of a proton, a single proton, with an electron circling around it. Well, when you remove that electron, really what it becomes is just a proton, or a hydrogen ion, if you will. So we can take water, split it apart right here, end up with a hydrogen ion, and also a hydroxide ion. Hydroxide. Hydroxide is where the O and the H are still connected to each other, but they have a negative charge because they've lost this proton over here. If I take a cup of water, and I were to split every single one of them and then let them all recombine, I'd end up with the exact same water again, right? What if I was to split them all, remove some of these, and then have them all recombined? There wouldn't be enough hydrogen or hydrogen ions to combine with the remaining hydroxide ions. There'd be an imbalance. This is how we create acids and bases. Let me show you an example. So they form when water ionizes, and they have incredibly important biological effects. Having strong acids and strong bases is very important as long as they are in the appropriate locations. They can totally screw things up if they are in the wrong places. So here's how we create acids and bases. Over on this side, let's say we started out with an equal number of hydroxides and hydrogens. Equal number. Okay? Equal number of H's, equal number of OH's. However, we add to that extra H's, but don't add extra OH's. Well, now there's a disproportionate number of hydrogen ions in this substance over here. If there's a disproportionate number of hydrogens, then it's an acid. If, on the other hand, we take that substance and we add extra hydroxide ions, then it becomes a base. And we can add a whole lot of these and make it a really strong base, or we can add only a little bit and make it a very weak base. Same thing over here. You can make a strong acid or a weak acid. And depending on how much or how little you put in, you can create a myriad of acids and bases that fall along a scale called the pH scale. This pH scale actually measures the number of protons or hydrogen ions that are concentrated in the fluid. And anytime the number of a pH scale changes by 1, it's actually an order of magnitude change. So when you go from, like, for example, 6 to 7, you have increased by an order of magnitude to by 10 times the number of hydrogen ions in concentration. And the scale goes from 1 to 14. With 7 being right in the middle and therefore being neutral. When you are at 7, when you are neutral, that means that the number of protons, that is the number of hydrogen ions, is exactly equal to the number of hydroxide ions, or OHs. And when you start erring on this side, that means there's more H's than OHs. And when you go over here, there's more OHs than there are H's. Okay? This is a strong acid, this is a strong base. And so therefore, acids, since they have a disproportionate number of H's, of protons, they are starving for OH's. They really want OH's. And the stronger the acid gets, the more they really want those OH's. On this side, it's the exact opposite. They are so overloaded with OH's that they are starving for H's. They want to come into balance. They want to go back to being water. Okay? So acids tend to donate their protons or their hydrogen ions when they are dissolved in water. Acidic solutions are less than 7 on the pH scale. And bases, they like to accept hydrogen ions when they are dissolved in water, and their numbers tend to be greater than 7. Remember this for the exam because I'm going to be asking you about strong acids, strong bases, weak acids, and weak bases. An 8, for example, is a weak base. a 6 is a weak acid. A 12 is a strong base, and a 3 would be a strong acid. And I thought I'd throw this interesting chart up here. It actually has a whole bunch of substances on them and gives you an idea. They've put right here in the very middle pure water. Pure water has an equal number of H's to OH's, and it's on 7 on the scale of 1 to 14, or 0 to 14, if you will. If you start going into the acidic side of things, up here is acidic. Look at that. Milk, slightly acidic. Urine, slightly acidic. Did you know that coffee was an acid? I'll bet you didn't know that bread was an acid, too. Well, you probably knew about lemon juice and those sort of things. Hydrochloric acid and gastric fluid. Gastric fluid is what's in your stomach. That's stomach acid. Yeah, those are all highly acidic. And you probably know them to be dangerous, right? You don't want to be pouring acids on yourself. That would be really bad. However, over here on the base side, you need to be equally careful about bases. Mild bases are not a big deal, just like mild acids aren't. Blood is slightly basic. Egg whites, seawater is slightly basic. However, you get down to stuff like this, hair remover and oven cleaner, you got to be really careful about using that stuff because it is highly dangerous, just as dangerous as it is over here. When you pour hair remover on yourself on accident onto your skin and you don't just kind of keep it onto just your hair, remember, it's starving for protons, and where do you think it's going to get those protons? It's going to pull them right out of your skin, which is how it can burn you. Over here, it's the exact opposite. You've got your gastric fluids that are starving for OHs, and they're going to pull them right out of your skin too if you pour that onto your skin. So don't do that. Very, very dangerous. Strong bases readily accept hydrogens or hydrogen ions. Sodium hydroxide is a great example, and it is the main component of Nair. Like this idiot who obviously used it and thought he was being funny. I don't know. I guess because it kind of does look funny. Weak and strong acids, they are reluctant hydrogen donors. Okay, weak acids are reluctant. They still donate it, but not like strong acids. They can also accept hydrogens after giving them up. For example, carbonic acid, and this is a good example that we'll talk about later in buffering. But we'll come back to buffering in just a second. Let's talk about strong acids, though. Love those strong acids. This is a great example of one, this bombardier beetle here. It actually creates an acid and it retains it in a gland and it sprays it at its prey or at its would-be attackers. And if you feel it, you feel like you just got burned. Well, you weren't being burned by temperature, by heat. You were being burned by an acid. And strong acids completely give up their protons as soon as they come in contact with something. Hydrochloric acid's a prime example. That's like stomach acid. If you've ever, had a fit where you were throwing up for a long time, yeah, and your teeth kind of feel gritty after that, it's because you've essentially, bathed your teeth in stomach acid, which is not really a good thing. There are also environmental effects of acids. Acid rain. Rain normally has a slightly acidic number to it. Naturally, it's about 5.2, which is a mild acid. However, because of industrial pollutions, such as sulfurs and nitrogen oxides that go up into the atmosphere, they end up making the rainwater far more acidic than it normally would be. There are cases in the Pacific Northwest all the way over to the New England states where you can actually get rainwater that is down to 2.4. 2.4 is like lemon juice, guys. That's like pouring lemon juice all over a forest. Not a good thing. Not a good thing. Okay, so I had mentioned this whole issue of buffering systems, right? And what this means is that your body has to be really careful, doesn't it? It has to maintain pH levels and not allow them to change very much. And that's actually very important. Slight changes in pH can actually do some very, very bad things. I mean, imagine if your stomach fluids were to accidentally spill out into the wrong place. Not good. So your body has come up with a defense. It actually has buffers. Buffers are substances that can combine with acids and bases and neutralize them or absorb their excess ions to keep the pH from changing very dramatically. And baking soda is a really good example of a buffer. And so sodium bicarbonate, that's what it's called. Keep in mind that you can actually use this in a lot of applications to neutralize acids and also to neutralize bases. So people actually use them in the back of their refrigerators and for cleaning substances. They are perfect. The last little example here of an acid and a base buffer would be this bicarbonate ion that exists in your body. I want you all, for the last slide here, this, by the way, this is the last slide. Yay! I want you all to hold your breath. As you hold your breath, your body is building up CO2. Well, CO2 is an acid. So does it stand to reason that if you hold your breath and you build up that CO2, that your blood is going to slowly become more and more acidic? Well, that's not good. You don't want your blood to become too much more acidic. So your body detects this. It detects the slight change in pH and begins to flood your body with this carbonic acid bicarbonate buffer system. So it floods your body and the pH doesn't change very much, and you should be very thankful of that. So when blood pH drops, bicarbonate binds to the excess protons that begin to float around, forming carbonic acid, and carbonic acid is totally safe. So congratulations for having that really cool system in your body. It's only one of the many things that we're going to now talk about. From here on out, we're actually going to go into slightly more complicated biochemistry, but equally, actually far more interesting too. So if you need to review this lecture, I know it's kind of a long lecture. This is an hour and a half long. Please do so. Go get some coffee, go get a thing of popcorn, and I will see you at the next lecture.